say we write y double prime plus 5y prime plus 6y equals 2x plus 1. So if I wanted to use the summation notation there, this would be a summation from 0, with the index going from 0 to 2. So 0, j would take values 0, 1, and 2. We would stop at 2. 2 is the order of the highest derivative in this expression. In this case, the operator L of y here on the right-hand side, what we have are coefficients using that notation. P sub 2 of x would be equal to 1, and then P sub 1 of x would be equal to 5, and then P sub 0 of x would be equal to 6. So in the notation of this linear combination, we're assuming the coefficients here are 1, 5, and 6. In this case, these coefficients are not really depending on x. They are constant, right? So each of them, 1, 5, and 6. This is one of those cases of constant coefficients for a second order linear differential equation. Now, in this case, we would write here, in this case, we would write Ly, or L of y, equals 2x plus 1. And by L of y, we mean that summation of 1 times y double prime plus 5 times y prime plus 6 times y. Now, so when we consider this operator L of y, specifically when we consider L of y equals something, right? We want to consider L of y, this is what we just mentioned here, we want to consider the problem we want to consider is L of y equals f of x. That's how we want to write the holiday in short form. L of y equals f of x. Okay, so L of y equals f of x. So here I'm gonna sketch this in two scenarios. Okay, so equal something over here, or this may be equal to something over there. Okay, on the first case, L of y may be equal to a function f of x, which is always equal to 0. If that is the case, if L of y equals f of x, which is equal to 0, that is a homogeneous problem. And with the solution, we're going to call the solution y sub c, and that c is going to stand for a name. We're going to give this as complementary. Solution. So the homogeneous problem now is going to have some type of nickname. More specifically, the solution, a solution to the homogeneous problem is going to be considered complementary. It's going to be dub name complementary solution. Now, if f of x is a function that is not identically equal to 0, then this is the so-called non-homogeneous problem. That's what we are really interested in. In such case, the solution is going to also have a nickname. We're going to say, maybe we're referring to one such function that satisfies the holiday. There is one such function we manage to find, for which when we evaluate that operator of linear combinations of derivatives of higher order, we evaluate that operator at that function, we get a match. That L of y for that particular function y is equal to f of x, where f of x is some expression. That function may be one specific function. It doesn't necessarily mean that it is the general solution. If one such function, we manage to find it, we're going to call y sub p, and this is because this will be referred as particular solution. So if we decide to set the right-hand side, f of x, being identically 0, the problem becomes homogeneous. We proceed as we had done before, specifically for constant coefficients, homogeneous problems. We assume the solution is of exponential type, translate that into characteristic equations, find the roots of the characteristic equations. They may have zero imaginary parts, non-zero imaginary parts, and so on, right? So we have developed some methods, techniques. It may be that it's not identically 0. That's what we're going to get into in just a minute. In such case, we're going to try to find one such solution. And when we find it, we're going to call it y sub p, which is called particular. So we have either complementary, y sub c, or particular solution, y sub p. Now, let's now consider a theorem that states the following. It says, well, let's consider the operator Ly being equal to f of x, where y sub c solves Ly equals 0, and y sub p is a solution Ly equals f of x. So really what we're saying here is, in parentheses, we're saying is that L evaluated at y sub z equals 0, and L, the operator evaluated at y sub p, equals f of x. That would be the hypothesis of this theorem. So we have one complementary solution and one particular solution. Then the general solution of the original problem, the general solution of Ly equals f of x, the general solution is y equals y sub c plus y sub p. In other words, you could think of this as being, you can think of here a coefficient of 1 in front of y sub c and a coefficient of 1 in front of the particular solution. And what we're saying here is that the general solution is a linear combination of the complementary solution and the particular solution. So this is no other thing than a linear combination of complementary solution and particular solution.